Welcome back to our latest TechBite series. In the past, Adnan has talked about some of our mid-infrared products, detectors and lasers. Adnan is back today to take this topic further. So Adnan, can you tell us what you're going to be talking about today?
Thanks, Victoria. As you say, the last couple of times I was here, I spoke in detail about our mid-infrared detectors, the multi-stage INAS. Then I talked about our quantum cascade lasers, both technologies that work in the mid-infrared region for optical gas sensing in industrial, medical, environmental, and automotive applications. So I'd like to take some time to expand on this mid-infrared family that we're developing here at Hamamatsu, and also explain what these technologies aim to do.
When you say mid-infrared family, I assume that's the title of this talk, Mid-Infrared 2.0.
That's right. Hamamatsu's technology developments can truly be seen as a 2.0 refresh of the mid-infrared space. Just like we had the evolution of Web 1.0 to Web 2.0, where you had first-generation read-only websites and technologies like Netscape, MSN and Yahoo, and they made way for more disruptive participatory platforms like Twitter, the Google ecosystems and Amazon Web Service.
Interesting. So how are Hamamatsu doing the same with mid-IR?
Well, let me talk first about what mid-IR 1.0 currently looks like. You have various industrial process control systems, often for gas detection, sometimes for temperature monitoring, for example, that use historical mid-infrared technologies. And when I say historical, they really can be considered a part of history. Take the pyroelectric effect that was discovered as far back as the 1700s. The pyroelectric detectors based off of that really met their technological maturity in the 1980s. Other 1.0 detectors will be comprised of harmful materials like lead and mercury and have strong environmental concerns. And for the emitter, something as simple as a hot wire is often used, cost effective and emits lots of blackbody radiation, but doing so very inefficiently. Our mid-infrared 2.0 family disrupts this space in various interesting ways. So I want to spend some time in this TechBite and discuss those technologies.
In the last TechBite, you discussed our quantum cascade lasers. Should we start there and how it fits into this 2.0 story?
Good idea, Victoria. Let me set the scene a little bit. Our viewers may remember from my last TechBite that I discussed how we were improving our chip's energy efficiency to really make a strong technology for OEM use. Well, there's another way that the QCL chips are used that's really quite interesting. Last time I explained how a Bragg grating is created within the structure of the chip to feed back all of the produced wavelengths into a single one. There's a well-known, though far from simple trick in the QCL market where you take this grating structure outside of the chip and create what is called an external cavity that the QCL chip sees, and that grating can be moved. This gives the benefit of a widely tunable source alongside the sharp single spectral line of the QCL itself. Gas detection systems based on this wavelength sweeping QCL can be relatively bulky. So at Hamamatsu, we've been employing our expertise in MEMS technology to produce the world's first MEMS integrated wavelength swept QCL, a device that is really quite tiny compared to its predecessors. The technology is still being developed to be ready for OEM mass manufacture, but we're really keen to see who'd be interested in testing this disruptive technology when it's available.
It's really impressive that the technology has been miniaturized so much. Are there any other emitter technologies that are part of our mid-IR 2.0 family?
There are indeed. Two technologies. One that's already well established, the other one is up and coming. But I have a very interesting demo of it to show our audience at the end of this TechBite, so hopefully everyone sticks around to find out. Before that, let me talk about our mid-infrared LEDs. These can be considered the 2.0 disruptor to the simple filament lamps that are often used for gas detection. We've been developing our ability to grow refined crystal structures to emit light in the mid-infrared. As such, we have separate LEDs for CO2 detection, emitting at 4.3 micron wavelength, and methane detection at 3.3 micron, with world-leading performance. The latter is particularly cool because anyone who's in the industry will know just how much less hydrocarbons like methane absorb in the mid-infrared compared to CO2. And this is where we really focused our development. Our newest LED having almost an order of magnitude higher power output compared to its predecessor. This means that they can make for long-lasting replacements to the old filament lamps using a fraction of the power consumption too. In fact, this opens up a wealth of flexibility when it comes to looking at handheld, battery-powered gas detection units.
That sounds like it would fit really well with our multi-stage INASP detectors.
They absolutely would. Once you learn how to set up your electronics to take advantage of the unique structure of these devices, you get all of the benefits of a solid-state device. Passive detection, no requirement for signal chopping, and great economies of scale. Not to mention that it provides high sensitivity without needing to rely on harmful materials like lead or mercury in its manufacturing. Again, this is the 2.0 revolution that offers eco-friendly alternatives to the historical mid-infrared detection technologies. However, everyone's watched my first TechBite will already be aware of the advantages of multi-stage INASP. I want to also show our audience how we've been improving it. People might be familiar with the concept of back-illuminated CMOS image sensors and cameras. This is where, to avoid electrical circuits that block the front of some of the pixel area, the chip is flipped around and the substrate is thinned, allowing it to image with greater sensitivity out of its back. We've applied this same kind of technique to our multi-stage detector. The value gained is not so much higher sensitivity, but much greater temperature stability. And this really fits with the theme of handheld gas detectors, where they need to work in rugged environments that vary widely with temperature.
So lastly, Adnan, you mentioned that you have a demonstration for a new light source technology for us.
That's right. Here we have a demonstrator to show off our new multi-stage INASP detector, and also here is our yet unreleased emitter technology that I'm really excited about. So before I tell the audience what it is, I should tell them about the 1.0 technology that it's disrupting. There is another kind of blackbody emitter that builds on the concept of that hot wire. You have complex MEMS structures that can be heated to high temperatures of around 500 degrees C and emit large amounts of mid-infrared radiation. Even though they are more robust and effective than a hot wire, they still suffer from the same issues in terms of modulation speed. Heating them up to temperature takes a while, so you can only modulate them at a few hundred hertz maximum. So this emitter here is the MEMS graphene emitter. A few thin layers of graphene that heat up to 1000 degrees extremely fast. So rather than taking a few hertz of modulation speed, you can achieve 3000 hertz of modulation. And this is really great because you can do away with a mechanical chopper within your gas detection system and still get high signal to noise levels from performing high-speed averaging and mode locking. So I want to show off this mid-infrared detector and emitter in this demo system where we have this gas cell and it will be filled with CO2. So here we have our mid-infrared detector, and that's all connected together to an amplification unit, and an oscilloscope is reading it off on the screen. And what you'll be able to see is that if I just blow into this cell here, you'll see that it's picked up the signal of my breath in there. And one thing to note is that because CO2 is heavy, I can push this down and you'll see that it slowly decays over time because the CO2 is filtering out. One thing that I'd love to show off is explosive hydrocarbon detection with this kind of devices. But sadly today I don't have clearance to handle explosive gas canisters in our lovely demo room. However, it's really simple to just change off the filters on the detector side and orient this kind of a system towards methane detection.
This is great, thanks Adnan. But before we sign off, would you be able to summarise what we've discussed here today?
Sure, Victoria. So today I've introduced Hamamatsu's Mid-Infrared 2.0 family. This consists of technologies that are available today, like our multi-stage in-as detector with its recent back illumination upgrade, making it highly temperature stable, a perfect fit to be used alongside our world-leading mid-infrared LEDs in handheld gas detection systems. Our multi-stage detectors can also be comboed with our quantum cascade lasers for various OEM applications, and we're continuing to develop this technology. I'm really keen to get our MEMS wavelength swept QCL into customers' hands once it's available and see what wonderful things they can develop. And the same for this graphene source. The fact that you get broad and high flux output in the mid-infrared light while still being able to modulate it fast is a real game changer, especially when it comes to gas filter correlation techniques. All these technologies culminate together into our mid-infrared 2.0 family. So we at Hamamatsu are keen to help industry to understand how to use these new technologies and help them both innovate and disrupt the markets that they work in. Please contact us via our feedback form if you wish to learn more about our mid-infrared 2.0 family. Thank you, and I look forward to hearing from you again soon.